I just want to have like a quick interactive discussion on what we discussed yesterday, just to see that everyone is comfortable with these concepts. So yesterday we went into a deep dive of these four state-of-the-art architectures: AlexNet, VGG, ResNet, and Inception. Can one of you tell me what was different in AlexNet and what it achieved over state-of-the-art at that time? Do you remember?
Yeah, so it's the first deep neural network.
Relatively deep compared for that, correct?
And they actually achieved from, I think earlier it was 25%, something they reduced it to around 17.
15, yeah. Oh, awesome. Okay, cool. And the other innovative things were they use ReLU, then dropout, what else? Inference time data augmentation, and crops, right? Random crops. So essentially basic level of training and data augmentation at the time of training and inference, right? Those were the contributions of AlexNet, and that brought the error down from about 25%. In 1 year, it was 25% in 2011, and it brought it down to about 15%, 2012. Yeah, this is a watershed moment, and from then onwards, we see that deep learning has kind of taken over the computer vision field. I think ReLU and dropout. I would think those two are the most critical. No, it was from AlexNet team only. Dropout. The paper was published, I think, in 2011 or so. The dropout paper. Okay, so I think AlexNet is, so everyone is comfortable with AlexNet. It was pretty straightforward, right? How about VGG? So VGG we still use at least the baseline level of models like VGG 16. People still use it for pre-training for their problems. So VGG, do you remember what the key additions were over other networks?
They introduced more, smaller networks are more actually in case of VGG.
Correct, right.
Yeah, and they used kind of
the increase in depth. The increase in depth of the network, right, as the layer depth increases. So that was one. Yeah, ensemble. Then, you guys remember a lot of it. Yeah. One more is the key thing in BGG is use of 3x3 filters, right? That was the key. That was the key takeaway from BGG. Just look at the summary. Right? So yeah, 3x3 filters, increasing filters, number of filters with depth, then scale variation during training and inference augmentation, then model ensembling, and this brought the ImageNet error down below 10%. Right? So that was the key thing. Okay, now comes the two killers. ResNet. Do you remember what was the key thing on ResNet? So what problem did it solve? See, already here the network depth was almost 19, right? VGG 19. Inception came slightly before ResNet, so that had 24 layers, or yeah, it had quite the depth as well. So what did ResNet achieve really?
The vanishing gradient, as the number of networks increased, really people doesn't see the improvement in performance. The ResNet's point was they really want to attack that problem to get that vanishing gradient problem to go away, so that they use a residual network rather than, because gradient typically multiplies as you do a double derivative.
Right.
So that's when they try to go with a different approach, which is the residual approach, to get rid of the problem of vanishing.
Correct. So you can think of this one, right? The networks before AlexNet as really shallow networks. Then AlexNet and BGG are medium deep networks, and ResNet is really deep, right? So the contribution of ResNet was to get the networks to train for really deep networks, where I mentioned that they even tried for a 1,000-layer network, right? So that was not possible. One is they solved the vanishing gradient issue, and it's not enough just that issue is solved. It is also the complexity of even if you solve that, the networks are still not being optimized, right? Because we discussed some concepts on convexity and so on. So it is still goes beyond the vanishing gradient issue as well. So they tackled that as part of it using the residual connections. Does everyone understand the intuition behind the residual connections? So this was the input, right? And this was your convolution block. So earlier what used to happen was this, the output of this was completely derived by this, right? So this is the output. Now it is possible that if this is somewhere in the middle of your, like, say 1,000 layer network, it's possible that the feature maps typically tend to go to 0, right? So this layer could completely drop out, right? So which means that it was not learning even very simple maps like the identity map, right? So that was the issue when they were trying to train on really huge networks. Then what they did a very simple thing of just copying this input here. So create one copy here, input, and then add this to so this is the residual. And then now the output is defined as the sum of these two, right? So they just did a minor change like this. So this, we saw that this idea is not new in the sense that it has been used in engineering and mathematics before, and even in optimization, right? We saw this idea of momentum and so on. So, but they were the first ones to think of it in the deep learning context of it, right? And we also saw some 1D examples on why that would make sense, right? When you add this, or even in least squares regression, for instance, when you add like a decay term, it has it conditions your inversion process, right? So in that way, this had a conditioning effect, and then it takes care of the vanishing gradient effect as well as the other optimization when you're dealing with really large networks, right? So that was a key idea in using residual connections.
This residual thing came into existence only because this was a deeper network. Right?
No,
having been a shallow network, you won't even have residual.
You can do it. Yesterday I showed an example of a shallow network where I used 2 residual blocks, right?
Yeah.
That would really not be necessary. If you're going up to AlexNet, for instance, you can just do ReLU should be able to do that trick.
Oh, that's what
But the problem is when you're going to say 100 layers or 200 layers, then ReLU is not sufficient. Because more higher order interactions come into being when you're going top down into VGG is medium deep networks. When you're going to really large, hugely deep networks like 100 layers, 200 layers, or 1,000 layers, then ReLU is not sufficient, right? You'll have to look at techniques like this. Or there's one more thing called DenseNet, which has also come. So you should read that paper. That's also very useful. Yeah, and the key takeaway here, yeah, so they also have done multi-crop and multiscale, prediction and averaging. The key thing in this one, in Inception as well as ResNet, was there's no fully connected layers, right? So which means that you save a lot of parameters here. Dropout is not used. Another key takeaway from this. Instead, they have replaced it with batch normalization in all the layers. Then, yeah, usual data augmentation and skip connections. So these were briefly error rate dramatically came down from about 7% to 3.5%. It's a top 5 error. Remember that first slide I mentioned it. The top 1 error, it will be around 80% or 82%. You need to check. Yeah.
It's only the top 5 error.
Top 5 error, yeah. No, that itself is significant because it is top 5 from 1,000 classes. Yeah, then in Inception, we saw this, right? So, Inception, we looked at the utility of 1-by-1 convolution. Does anyone remember what is the utility of 1-cross-1 convolutions? Yes, think of it as a dimensionality reduction, right? And it also helps because you're doing dimensionality reduction in depth. You can also, it saves computation, power for you. What about, the Inception module, did everyone understand on at least the motivation for that?
Not affecting the image information, but reducing the.
So this, I hope these motivational examples are clear in many things, right? So the architecture design has to be handcrafted, meaning that in some problems you may not actually need all the channels. Just an aggregation of the channels is sufficient to make the decision process, right? In something like this, you know that this object, you can just make it out by just looking at a grayscale image. So this is one possibility. In one of the problems, maybe this learning problem, this might be the situation. In another, maybe the kernel size needs to be chosen differently. typically you see that the kernel size is handcrafted, right? It is 3 by 3 throughout your network. So that need not be the case, right? In some layers, maybe higher order kernels might be useful. Next is in what do you need pooling or not, right? The other decision that Inception allowed. And once again, this used to be handcrafted, and then Inception had an automatic way of doing this, at least from data. So, which means that to handle at every layer, especially if you are looking at really deep layers, it's very hard to optimally choose between these design choices, right? So that motivated Inception to look at 4 different paths that the algorithm can take in each layer, in each of these Inception layers. So 1 through 1 cross 1 convolution. So can I solve the learning problem by just taking a linear combination of the previous layers feature maps? Can I work with just a small kernel, or do I need a larger kernel? And lastly, can I just work with just a downsampled version of the previous layer, right? So 4 decisions that the algorithm can take based on data. Earlier, each layer you had to optimize it by hand. You can do it for 10 layers or 15 layers, but then if you're going into hundreds of layers, it's not possible to do it, right? So nowadays, that's why it explains the success of Inception plus ResNet architectures, right? So to go beyond to really huge networks, you need something like skip connections. And then because you don't want to really optimize you don't want to handcraft your architecture for like hundreds of layers, right? So you need something like an Inception block to automatically choose the correct path, right? So that's why Inception plus ResNet type of architecture is quite successful in today's state of the art. And this you understood, right? Where because you have too many parameters here, there are some 1 cross 1 demonstrative reduction tricks which is done to reduce the number of parameters for Inception. And then global average pooling. Once again, yeah, the motivation is you're anyway dealing with really huge networks. So why not just leave the representation to the convolutional layers, which are really deep anyway, and take out the fully connected layers, which are just increasing the number of parameters. Right? So that is the motivation. Of course, when you're dealing with say a shallow network or like a medium network, the fully connected layers are important. But then if you're dealing with a really huge depth network, there's already enough of representation power there where you probably don't need a fully connected layer. Which is why they just work with global average pooling. But then when you're dealing with small amount of data, it's likely that you'll notice that you may not be able to work with just average pooling, right? You probably need some amount of fully connected layers. So the key takeaways are the Inception modules, no use of fully connected layers. So that saved the number of parameters. Then similar kind of thing, multiple crops, and then ensembling. And finally, it moderately brought the error down from 7%, right, compared to VGG. So today we're going to look at a very important aspect in the field called transfer learning. So you see that modern architectures, as we started to motivate, right, modern architectures are really deep. And they need a lot of data to train from scratch. And also realize that data and labeling is expensive and time consuming. So yesterday I gave an example of in X-ray, for instance, right? If you want to get a labeled image, it might cost you anywhere from 50 to 100. And because resolution of the images is 2K by 2K, and you can't afford to downsample it to 256 because you'll be missing some very critical disease indications. So you have to say you're going to work with 512 by 512 or 1K by 1K dimension data. You need that much of training data to prevent it from overfitting, right? Or to get the features from it. So which means that unless you have like 500K or a million images, you cannot really productize your algorithm. So it is too expensive to train from scratch. So if you see a small to a medium sized startup, they will not have this kind of flexibility to acquire this amount of data and then train from scratch. Even a big company, for instance, right? So the thing is, can you do something about it? We know that modern architectures are really deep, and they have used a lot of data from open source like ImageNet and so on. but then we are looking at different domains, right? So is it possible to utilize that knowledge for a different domain is what we're going to talk about today. It's called transfer learning. In addition to a small data scenario, you also have scenarios in surveillance and retail, right? Where you have large amounts of video data, for instance, but then there is no expert to sit down and label that. So then you will be typically looking at problems like event detection and so on. So even in those cases, it's very hard to train a network from scratch. You want to utilize whatever is there pre-built and then go from that. Use that as a starting point. So the idea here is that given a new application, one wants to look at reusing knowledge from those architectures as well as weights, right? So that's briefly what we want to do with transfer learning. Now, if you intuitively think about it, that's what human beings do, right? Now, suppose you have learned one language, say C or C++. It is very easy to pick up Python, for instance. So scaling up across even programming languages as well as just spoken languages, you become better at it, right? Similarly, skills like if you're already good at riding a bicycle, then you can easily pick up riding a bike. So things like that comes very naturally to us. But then right now, it's still in the state of research for machine learning and deep learning, right? Because typically what happens is when you move to a new domain or a new problem, these algorithms forget what they have learned before. And then you again put it back, then you would have it'll underperform in your original problem, right? Which is not what you want. Say you have deployed some algorithm in a site, and then you start to get more data, or you get data from another site, and then when you deploy that new site, you see that your algorithm is underperforming, right? But then so you retrain with that. Then you go back to the first site, then that would be underperforming now. So this is called a problem of catastrophic forgetting, right? Which has to be taken care of. So transfer learning is still a problem which is in the research state, but a lot of people are using it. So it'll be so a lot of companies nowadays, you see that when people are scaling up the number of applications, right? So when you're building, say, 5 to 10 applications, it's fine that you might have a lot of data for that. You can look at these applications in a point application type of basis. You can build them independently. But then if your company, as you acquire more data and you scale up to, say, 100 applications, your stakeholders are not going to wait for you, right? They're not going to wait for months before you can develop an application. They're going to ask, you already spent a lot of time in building these 100 applications. Why are you still taking so much of time, right? So which means that as you scale up, you also want to somehow utilize the models that you have used in these 100 applications when you're building the next application, right? And it is also not feasible to use suppose I've used in my 100 applications, I've used, say, 100K data. When I'm looking at the 101th application, I just cannot use the raw data, right? Just imagine in 100 applications, I'm going to have 100K data. I don't have the resources or even the algorithm flexibility to use the raw data. So I must have some way of reusing the models, right? So all of these applications have been encoded as some sort of a model repository. And when a new application comes, I need to somehow know how to pick that, right? So that is an active field. You see from Uber to Ola, all of them are having their own platforms where they're building model stores and model zoos, right? From where a new model, they are quickly build it from their existing repositories. Catastrophic forgetting. So you've trained the model on some problem, and say you're getting a new set of data from either the same domain. Maybe when you get new data, always there will be some variations, right? Or when you're getting new set of data or your tasks change. So today you're looking at recognizing 4 objects. So tomorrow you want to bring a different type of category. Now you train for that 5th category, it'll forget what it had learned in the 4 categories, right? So that effect is there. It is still in the research mode where people are trying to address that. So earlier when the data explosion was not in vogue, right? So people typically looked at point applications, which means that you had these point data sets, specific data sets, and you build applications for each of that, right? Traditional approaches. And traditional approaches were good enough for this. Because anyway, these were small amounts of data and then you could build on that. Now, as the data sizes are really blowing up, and like I was saying, the thing is the demand for the delivery time is needs to be shortened. It's an urgent need to actually expand on the knowledge that you have gained out of previous tasks, right? So in transfer learning, you're looking at a scenario where you have a bunch of applications you have built, and you want to encode this as some sort of a knowledge base here, and then utilize this when you're building a new learning system. So that is the idea here. I mean, it's very easy to put it in a slide, but there is a lot of research work which goes into it, and it is not there. It's probably still in its infancy stage on trying to achieve this. So let us say that for an example, we have this MNIST data. So we have large amount of data, and we have built a model for classifying from 0 to 4. These 5 digits we learn how to classify. Now, and see, one more note that I want to give here is that for the purposes of discussion, we are just going to look at supervised learning, because you can also bring in semi-supervised and unsupervised learning also into this whole mix. That will get a little more involved, right? For now, we'll assume that the target domain, there is supervised data labels, and it might be limited in number, and then you want to see how to do that. So given that this is your source application, a source model that you have, let us see what are the different scenarios that one could have. Right? One is, let us say you want to build a classifier to classify digits 5 to 9. The first source task was from 0 to 4. Right? So you can think of this as so it is a similar domain but a different task. Right? This kind of scenario. So here. Once again, we have two possibilities, right? One, you have a good amount of data here, and then less data. Even when you have good amount of data, I told you, right? So you can't afford to train from scratch, because that will take a long time to train. So when you have good amount of data, the thing is, can you give a bump up for convergence? When you have small amount of data, you want to complement the data in some way, right? So in both scenarios, transfer learning would be is essential. So let us say that this is our target domain. So this is one problem of where you want to apply transfer learning. Right? Can you think of other examples?
NLP kind of thing. So typically, like we have natural language processing, there is a fixed set of vocabulary. So I train it with whatever available in the literature vocabulary. Now I want to use it for my technical domain. I have a lot of technical words which comes out of my technical domain. So I want to do a kind of add those words into the training set so that it can start recognizing those words.
Yeah, we also face it in medical. So typically all the repositories are non-medical, and you want to utilize it for medical repositories. That's important. Anything else in image, in computer vision images where you encounter? No, at least in healthcare, I can think of that. So today I'm going to talk about one such problem. So we have enough of data on say X-ray general diseases, right? There are general diseases like you could have your cardiomegaly, which is an unusual expansion of the heart, and so on, right? You have general diseases or collapse of the lung, but then you have a specific diseases which are not seen before, like TB. So TB is more in India, right? It's an India-specific type of disease. So you built a model for a Western population, and then you want to use it for India. Then before you do that, you have to build. It has to support TB. Right? So in that case, you will have. In that problem, you also have a moderate change, because ethnicity, the type of the data will also change. But you also have to accommodate for the additional task which has been added, which is detection of TB. So what can you say about the reusability of low-level and high-level features here? Now, just think of this problem intuitively, and think of like the deep neural network that you have learned, right? So, and you know that in a neural network, at different layers encode different hierarchy of information, right? So, which part of that information is relevant for this problem? So, what do you think? So, which part of the network would be more relevant for this problem? Now, suppose I just want to move the network from which I've learned on 0 to 4 classifier, I want to move to this problem. I have many choices, right? I have multiple layers in that network. So which layer should I focus on more? In a neural network, what does a lower layer captures, right? It is capturing information very specific to the domain, right? And then it is extracting features from it, and then it keeps encoding higher order information, and then towards the classifier, it is abstract features, right? So here you see that in this problem, low level features are more likely to correspond to what we learned in 0 to 4, right? It will be like edges, corners, and so on. So the higher order information is going to change here. So here you can expect that it is the low level features can be transferred, right? And you probably need to tune your high level features. In this case, yeah, even here, right? Here you probably don't even have to change your low level layers. You can use them as
edges and all those things will
be remaining the same, right? So
here features only we
need to change
because of the design.
Because of the design for this problem, you need to change that. Yeah, right. So this is clear, right? I hope this scenario is clear. Just want to see if it is relevant for your domain. Right? The other possibility is, let's say you want to build a number plate digit classifier. I want to recognize this number plate, right? So you see that so what has happened here? Your domain has changed, right? The appearance of the source image has changed from what looks like a MNIST data, which is binary, to something like this, which is a color image. So which means that your bottom layers need to be changed, whereas your top layers need not be changed, because the top layers, hopefully your neural network would have learned the abstract features, would have learned to abstract these numbers out, irrespective of the domain. So here it is actually the opposite, where you probably have to tune your bottom layers, and your top layers can be moderately tuned, right? Because the MNIST data is handwritten, and here it is all printed numbers, right? There still be some minor variance. So this is another problem called domain adaptation. This is also very useful. Domain adaptation also, you can think of it in terms of online learning. Say I've deployed an algorithm in a site. I'm moving the algorithm to a new site. So there'll be some minor variants, right? Maybe I'm using a different scanner in the new site. So the noise properties might be different. So the appearance of the image might be moderately different. And we know that neural networks are very, susceptible to that, right? Even minor changes that appear outside of the training data can throw it off, right? So domain adaptation is once again is very useful for online learning and for multi-site learning and so on. Can you think of other examples here? This kind of appealed to me and the other one is multi-site learning, which I can think from healthcare. Anything from your domain you think is?
Is there some tool or something which will help us to know whether the transfer link can happen from the lower layers or only the higher layers?
It's more from the domain experience, right? So here, when you just visualize a couple of images, you know that the image appearance is different, right? Image appearance is different, and towards the end of it, your numbers, hopefully your network is powerful enough. You have learned the source domain on enough of data so that it is able to move out of those low-level features and has learned some abstract, I guess. In that feature representation, you're hoping that the 6 here and the 6 that you see in MNIST will have very similar representations. Right? And so from a domain knowledge, you kind of expect which should vary first. Yeah, you're right in the sense that if you blindly apply, we'll talk about some ways of doing transfer learning. If you blindly apply without using the domain knowledge, it may not work as well. So you'll have to know, which part of the network to tune and so on.
That's more like, you have like multiple features, right? Lower level features, where you keep going to high level.
Correct.
So you make a checkpoint at every possible intervals of time. And say in this case, I will have to have my own lower level features, but my higher level features would be goes from my earlier model. So I need to know, okay, from which checkpoint I need to plug that value and put it into my model.
Right.
Am I right?
Yeah. So, I guess that can be automated, but we'll be operating in that supposition, right? So we are going to segregate the network into a lower part of the network, middle, and higher, and then see which of the scenarios would fit into which of these possibilities. Okay, the third scenario is when you have a different domain and different tasks. This is most likely the application that you would have encountered, right? Unless if you're doing online learning on an existing product already, right? So the example here is you've already built this MNIST classifier on 0 to 4, and now you want to build an alphabet classifier by using that. So here you see that maybe at the basic low-level features you'll have some commonalities, but then as you go higher up, the abstraction will be different for what you consider an alphabet as well as for the number, right? Even the number of tasks definition also is different. So this is more likely the problem that we'll encounter, and it is that's why it is challenging. But luckily, at least the appearance of the image is not so dramatic. It is binary. It is still binary. The image characteristics is not that different. So yesterday we saw a lot of these state-of-the-art architectures were built on ImageNet, right? Because of the huge amount of data that they have, labeled data that they have. And very surprisingly, even for very different domains, ImageNet weights have been successful. So borrowing architectures as well as weights from ImageNet trained networks still seems to work on these different domains. Of course, the caveat here is that at least my personal experience is for solving, say, an X-ray problem or this fundus problem, you'd need data in the order of at least like 10,000 or 20,000 even to apply transfer learning. Otherwise, it's see, the thing is when you're running a network, you might see that you get a moderate improvement, right? It may be like you'll suddenly be excited because you got a 2% AUC jump. You run it 5 times, you'll see that will be within the standard deviation of the so whatever jump you're getting is more likely noise. So you want to make sure that you analyze your performance thoroughly by running it multiple times, similar to like a k-fold validation that you would do, right? Especially in the case of small amounts of data. When you're dealing with, say, less than 1,000 data or 5,000 data, you want to do that. So what is a problem here, and what is the need for transfer learning here, right? So this is still a classification problem. In each of this, you will just be, is that a disease or not, right? That will be the problem here. In addition to that, you might be required to mark the location where the disease has occurred. So in some ways, the problem is relatively simple. But as I mentioned earlier, data is only in the order of thousands at the max, because data is expensive in many of these domains. Getting the patient consent and getting the data is very expensive. But pixel resolution, which you need to identify small artifacts, when you consider that, the pixel resolution runs into the order of millions, right? So there is a huge dimensionality imbalance, right? So because of that, training from scratch is often not feasible in these domains, right? And also you have to take multi-resolution approaches. So this you can try. So what we have seen so far is we just train on one resolution, right? But alternately, what you could do is you can train on 64 by 64, take the network for the next resolution and so on until you hit 512, right? So these multi-resolution approaches are very, very popular in domains like this, where you're dealing with high resolution data. So in your domain, if you're encountering high resolution data, make sure you use some sort of multi-resolution approach. And if you just blindly downsample it and use it, then you might miss some serious artifacts. So here, one possibility is, can you adapt the VGG network, which is trained on ImageNet, to classify the above data, right? So that is the problem here. So the next one is what probably you saw this morning, right? You had a session on object detection. So once again, there is a huge number of applications around object detection and classification of putting bounding box, right? And then classifying those objects within the boxes. So surveillance or agriculture and so on, right? Or general computer vision applications. So here, you probably will have just a few thousands of images where you have the bounding box annotations and the labels. But then it's a challenge here, right? So here you see that this combination of people might never appear in another image. So even there, that the number of samples of this particular scenario is very limited. You might just have 1 or 2 samples. So once again, here the training from scratch is completely ruled out. So once again, here you would have to use a pre-trained network. So typically what you would do is you adapt the VGG network, which is trained on ImageNet, to build a object detector come classifier, right? Yes, so you have to give maybe like 1,000 images with those bounding box annotations. You don't have to give variations in locations or something like that. So these algorithms, they give proposals. You must have heard of region proposals, YOLO and so on. They give proposals where they do the search thing very efficiently, right? So you have to give multiple images with this bounding box and labels, and then the algorithms will take over from there. So even if the objects are in different locations, they'll still be able to capture it. But there are some details to discuss. We'll do it as part of the next session, right? So next session, we'll be looking at object detection. So the third problem is segmentation. So once again, segmentation, you see that now you're dealing with, in many applications, like say path planning or in this one, right? In what do you call it? For automated driving and so on, you need to delineate objects with sufficient resolution. But then you won't have enough of labeled examples, because even if you look at one or a couple of images, right, it is very hard for an expert to sit down and draw the boundaries for each of the objects. So you can expect that the labeled data will be very few in number. Then in medical data, once again, you have the same thing. Now, the thing is, in medical data, it's compounded by 3D effect. So now you have these images which are in 3D, and 3D it is even more difficult to get those segmentation boundaries. So even here, you should not be starting from scratch. You should be reusing what is already built, and then adapt this to build a segmentation type of network, right? What we call as fully convolutional networks, which also we'll hopefully see sometime. Yeah. Okay. So there are two advantages of transfer learning. One is the limited data scenario, where to get a good to overcome overfitting challenges. And next is, even if you have large amount of data, you want to get a higher starting point, right? Like I give you the example of in your company you have multiple applications. So for the next application you build, you need a higher starting point. You can't start from scratch again. That will not be a smart thing to do. So so the objective of TL is, can we get a higher starting point where it offers us a computational advantage as well as a data advantage, because data is expensive. Labeled data is expensive. So the common ways to do TL. Let's try to understand this. So this is your source domain, and you've trained a network. So remember from the first session's discussion that what does the network do? The DL network do? It automatically learns the dimensionality reduction or the low dimensional representation from the data. So it does feature extraction automatically, and then you have so it does the feature extraction in a way that it can be linearly separated, right, by this classifier, or with some moderate non-linearity. So that is the idea of DL. So you can think of two buckets here. One where you have a classifier, and then you have a feature extraction layer, which is represented as convolutional units. Right? So you have these two things which you have learned on lots of data. Now, question is, how do you reuse this for different scenarios that we discussed? Now, just I think you must be familiar with this. You had this visualization session, right? I hope you had a lot of examples like this, where I hope you kind of understand that in a neural network, in a deep neural network, so typically you have low-level features like edges and corners, etc., captured in the low-level, in the bottom layers. And as you keep going up, it gets more and more abstracted, right? And then you start to see parts of objects and groups of objects and so on. Finally, which ends up in a classifier, right? So we also have this observation in this behavior which we observe in DL. So with this in mind, what are the ways that we could do transfer learning? One is we could simply use a feature extraction, right? We can use like what is usually done in object detectors, for instance, right? So you have, say, this is your new problem. You have a new problem. You have a limited set of images with labels, right? Let's say you have 100 images with labels. Is a new problem. Now the question is, how do you build a classifier out of these labels? What you could simply do is, you remember that you had this convolutional base which you have learned from the source domain. You could just pass the input for the training examples of the current domain. You could pass those into this convolutional base, extract the features. So now for 100, you're going to have a scenario like this, right? So your problem, this is your new problem, this target, right? For this, you had images as well as you had labels, right? And you had, say, 100 of them. Your n is 100. Now, what you can do is you can translate this problem by applying, passing these images through the source domain's feature extractor and convert this problem into having 100 features. 100. So you can convert this into a set of features and set of labels, where n is 100 as well, right? Which means that this will be more like the problem that you have learned in machine learning, right? So you will have your feature set where n is 100, the number of samples is 100, and the number of features here, if you remember, maybe in 4096, for instance, in one of the networks, right? So the number of features that you will have for each of the samples will be 4096, and for each of the samples you also have the labels, right? So you also have the labels. So now you can deal with this as a regular machine learning problem and build a classifier on top of it. So that is one way to do it. But typically you would use it when you have less data, because then if you have even a few hundreds of data, you want to see if you can tune a little bit of the upper layers of the network, or even in the classifier part of the neural network, right? So you could do that. So typically when you have less data and when you believe that deep learning is not going to work here, you can probably even do this. Or even to build a first prototype, you can just simply do this, right? So when you don't have a GPU resource. So what will be the risk of putting this through DL? Let's say that you had very little data, but you didn't have a GPU resource, and say you're working with BGG16, right? If your only goal was to learn the classifier part of the deep neural network, you still have to pass all your images through the network and then learn the classifier part of it. It is still memory intensive, right? It may not even fit in your memory, and it may take a long time. Whereas the operation is very simple in the sense that since I want to learn only the classifier, if I can extract the features and even build a DNN separately, so just pull it out of it and then learn it separately. That itself will be useful. That will save compute time and memory for you. So this is one key thing. I've seen a lot of people do this mistake in the sense that they want to learn only the classifier, but then they still pass through the entire network. So that it might still take a day for you to train. You don't want to do that. So the other, so you can also use it within the deep learning network itself. So there are three possible ways that you could do it. Remember that so this is your, let us slow down for a moment. So here, this is your source domains network architecture you have. You've already borrowed the weights, right? The weights, so weights are sitting here at iteration 0, epoch 0. Now, what are the ways that you can fine tune this network based on the current data? So you get this, right? This architecture and weights are from the source domain, right? Whereas the input image, the training data is from the current target domain, right? That is clear, hopefully, right? Once you do that, you do the same thing, like what you do in neural networks. You start with some initial guess, right? Some random initial guess. Instead of doing that, you take the old architecture and start with that guess which you got from the source domain. Right? So there are three ways you can evolve the network. One is you can tune the entire network itself. Right? This obviously you can guess that it will be when your domains are completely different, or you have large amount of data. Otherwise, how do you tune a ResNet 1000, for instance? It's not possible to do just 100 images, right? You cannot do that. So when you have really large amount of data and you believe your domains are really different and you cannot do any transfer learning, then you can maybe do this and just do it for a few epochs maybe. The other strategy would be that since we see from our observation that the bottom layers mainly capture low-level information, right? Like edges, corners, and so on, which are more likely to be consistent across different applications, right? You can freeze this. You can freeze these bottom layers and only tune the top convolutional layers as well as the classifier, right? This would be this case would be when you have moderate amount of data, or you expect that your domain is more or less similar, right? Maybe just your tasks are different, but your domain is similar. We saw that examples, right? In the beginning. The third possibility is you freeze the entire convolutional layer and just tune the classifier part of it. So this would be when you have really a reduced amount of data, or your task is different, right? Or your domain, your domains are very close to each other. Just maybe your task is mildly different, right? In that case, you can utilize this. So this is what you would hope. This is what you would hope when you have built an application of, say, in your company you have already built 100 applications. So you want to do something like this, right? When a new application comes in, hopefully this thing is going to remain stable, and you don't have to tune this entire thing. You only have to tune this. So tuning this, you can find some faster ways of doing it, right? So this is what you want to get into, some sort of a model zoo, right? So just to summarize what we just discussed, so you can put this in, you can map these four possibilities into these four techniques, right? One is you freeze, the first thing is you freeze the convolutional base. This would be when you have a small data set and it is similar to your source domain. And then next possibility is you freeze most of the bottom layers and just tune a little bit of this. This would be when you have your data set is slightly larger and also the domain is similar. And third possibility is you freeze only the first few layers, because these layers are more likely to be consistent across domains, right? Then when you have a small data set and that is different. And lastly, when you have large data set or your domains are completely different, you think of ways of training the entire network, right? So this should be your last possibility, last resort. Any questions on this? Then I hope you already know how to code this, right? You think you can code this up in your neural network? It should. But I would kind of recommend you to read. There are some very good survey papers in transfer learning if you're interested in this. So in 2010 there is a good transfer learning survey for traditional machine learning, and I think 2012 or 13 there was a good transfer learning survey for deep learning. So look at those two papers. You will get a more so they have tried to define it in a more methodical sense. But now you see most in fact all of the deep learning, transfer learning would operate in this kind of framework, right? So typically you would start by tuning the top layers, the classifier layers, and then move up. Okay, a quick summary before we move into the notebooks. So the four ways that you could do it is, one, when you have really less amount of data, you extract features using state-of-the-art networks and learn the ML classifier only, right? So this is one possibility. You can extract the features and train a SVM or a random forest or whatever, right? The next is you can transfer the full architecture from state-of-the-art networks and then do it in terms of the four possibilities that we had, right? Third is and all of these networks are trained on ImageNet, right? So more likely it will not match with what we are working on, the domains that we are working on. So it is more preferable if you had some related problems in your own domain. So that is the example that I'm going to deal with in the notebook today. So if you had a similar problem which you had learned with a relatively larger number of data, you can think of reusing it. You'll hope that there's a bigger performance gain you will gain out of that rather than using ImageNet. Or in ImageNet, what you could do is use ImageNet for low resolutions to initialize your weights, train it, and then when you get to higher layers, use the one which you learned from the domain, right? So you can do things like that. And finally, don't forget to ensemble. Right? Okay, so the plan for today's notebook session was, just a couple of practices which people use today. One is fine-tune only the classification layer. Second is you can you fix the classification layer and fine-tune only the convolutional layers. Third is you can fine-tune the entire network. Fourth is you can do it in a step-by-step process where you tune the dense layers first, hold that fixed, then tune the convolutional layers, then you tune the full network. Right? You could do it in this way. So the idea here is that initially to start with, it's possible because DL is learning representations, but it's very specific to the current problem, right? Even if you have like minor changes, it is possible that for your application it may not work. So what you do is in that case, where your domain is same, you just tune your dense layer first. It just adjusts the classifier slightly, and then if necessary, you then tune your convolutional layer. If you blindly start with just tuning the entire network, you will, if all the layers, and you know that where are the gradients very strong in the classifier part of it, right? So in the first few epochs itself, your classifiers will go haywire, and you lose whatever learnings you had earlier, and it will run into catastrophic forgetting. So one way to deal with it is tune the dense layers first, right? That I mentioned, right? Catastrophic forgetting, meaning that you've learned on a source domain. Now suddenly when you're trying to learn on the target domain, for instance, it especially when you have less amount of data, right? There are two problems. One, it occurs, it overfits on the target domain. Second is when you take it back, when you take your network, you would hope that when you have learned on two domains now, source plus target, it must perform better on the source domain, right? You'll notice that when you train on the target and go back to the source, it will perform worse. Like a human, like what does a human being do, right? So you have learned to ride a bicycle, then using that, of course, you know how to ride a bike. It's like you've ridden a bike for a few years and then you've forgotten how to ride a bicycle. So it becomes like that. And another key thing which is essential for tuning the networks during transfer learning is you have to pay attention to the learning rate, right? And preferably, in fact, I've used Adam or RMS prop, but typically you would want to just go back to SGD and just tune parameters for that learning rate, momentum, and so on, right? So just carefully put that for your problem, because then you don't want to lose whatever you have learned in the source domain in the first few epochs itself, right? If you're using something like Adam. Yeah, but if you want to use those optimizers, just make sure that you set your learning rate to be pretty small. Then the other popular way to do it is using a differential learning rate, meaning that across layers, although in Keras it is slightly difficult to do. So what you do is, so you expect your features to be more consistent in the bottom layers, right? And as you go up the top, it becomes more specific to the problem. So instead of using, so what is the drawback here? If I use a small learning rate throughout the domain, then nothing much progresses, right? I may not get that much of a jump. But instead, what I'll do is I'll use a higher learning rate in the top parts of the networks and slowly kind of progressively decrease the learning rate as it goes to the top, right? So that's called a differential way of. So the advantage of doing that is you don't lose your learnings, and also you also get the gains which you get if you do. As against just using a constant learning rate, small learning rate. So I thought so the way which will be very useful for this course. So I want to just cover two case studies and make sure that you know how to solve these problems by the end of the course, right? So one problem which I want to take up was X-ray classification, right? We'll go end to end in this problem. Next one, and whatever I left out this time, maybe we'll remaining parts of the details we can cover in the next session. The other one I wanted to do was on face recognition, right? So next time we'll cover something on that. Right? So we should be able to, based on object detectors that we build, we should be able to build a face detector and some sort of a recognizer, at least in images, if not at the video level. So let us start with this case study. So as you know, TB is a prevailing problem in India, right? So now you see that building a TB type of classifier is a very useful algorithm for many government hospitals here. So what are the challenges here, right? So the problem is, given a TB image, an image which could be normal or which could have TB, you need to detect if it is TB or not. So one application for this is in a hospital where there is in a general screening type of application, right? There would be a huge number of normals that the doctor has to see, right? And he'll have very little time to spend on abnormals. So if you can just do a normal and abnormal classifier, so you can just push all the normals to the bottom of the stack and then the abnormals to the top, right? So it'll be useful for the workflow of the clinician. The other, yeah. Yeah. Yes, that's an excellent point. So now you see that most of the classification is going towards a multimodal type of. So what you need to do is it's not enough if you just classify using an image. So you need to take the demography, ethnicity, his lifestyle. See, for instance, a smoker will have a different appearance of the lung region itself, and it might look really with a lot of opacity and so on. But a clinician might recognize that it is a normal scan, right? So depending on the age, gender, ethnicity, symptoms, and lifestyle. So all of that has to be taken into account when you're doing. So you have to do more like a multimodal classification when you productize it. So this is in some sense we are not going to do multimodal classification here because we don't have the data, right? So if you have the original header information and you've integrated this into the hospital information systems, you can pull out all those data, EMR data, medical records of the patient, and so on, and integrate it into your classifier, which is what you should do when you're looking at this. So the challenges here are there is a dramatic amount of shading effect, right? And also you'll see that the shading effect is really varying across the patients, right? So normal appearance variations has to be tackled. Next is the diseases are small or subtle, right? You could have some small nodules, or you could have strand-like objects, right? So which means that you cannot downsample it like what we do for the ImageNet. Probably like you see in the dog breed classification. So too much of downsampling, you may not be able to recognize subtle differences between the classes, right? So this is one domain where you have that problem manifested in a serious way. So next is you also have some normal structures which are hiding, diseases like ribs, the clavicle, and so on, right? You could have diseases hiding behind it because X-ray is like a projection modality, right? Then resolution. So like I mentioned earlier, you're not working with millions of images. You're working in order of thousands, while the resolution of this image is 2K by 2K, millions of pixels, right? Then huge shape variability. Like when you're talking about different ethnicity, gender, age, and so on, right? The normal appearance variations itself is huge. What else? Yeah, limited label data is a common scenario, and high accuracy for deployment. So this often the killer for the application, right? So who are you competing with? You're competing with a radiologist who has spent 20 years looking at such images, right? He would have already seen like lakhs of such images. Do you think an algorithm which is trained on a few thousands of data can beat him? Even if it is done on your most fancy DL algorithm, it's not likely, right? So the algorithm is more likely to fail in the field. So maybe initial stages when you have small amount of data, you want to see how you can couple with other information, right? Like patient information and other. So you have to make your information more richer, or you look at a problem which is easier. Easier in the sense that easier is not in terms of acceptance, right? Now suppose you're working in surveillance, you have like thousands of hours of video, and no human probably can do that, right? Can replace it. And your algorithm can add a value if you can just build a little bit of accuracy on top of it. And same in retail, you see that there are a lot of areas where you can build these algorithms, and the accuracy need not be high to make a difference, right? So you need to look at those domains as well, right? You can merge it, yes. Yes, you can do that. But there are some scaling. Yeah, you have to take care of some scaling issues. But those are standard things in machine learning, right? When you're dealing with categorical data and data from different scales, you will have to do some scale standardization before you apply to a machine learning. No, it is something like suppose you had a machine learning problem where you have you're trying to classify based on lab data. You also want to add demography data to it. So what do? You just append that vector to that, right? And make sure that each of the variables is properly represented in terms of its scales. You can either put it within CNN, or you build a separate classifier for it. No, you remember that the first method here, this was, so this could be CNN features. You pull the CNN features out. You can also have HIS features coming in, medical records, lab data, and so on. So you just couple these features and build an ML algorithm on top of it, right? That's right. So that algorithm will take all of this into account, image information and demography and so on. Right? So this sort of algorithm is more likely to succeed than which is based on purely image information for the reasons I just told you, right? Because humans are naturally very good at perception. It's very hard to beat humans in our perception unless you have millions of data, right? Which we had for ImageNet. So what is before we go into this problem, right? What is the data that we have for this? There's open source data that I found. So the problem here is you want to classify this into TB versus non-TB. Right now, I don't have demography data where you can put that information in. So that I found there is a repository from China. There are 600 images on this, which are labeled as TB and non-TB. There is, because of NLP and so on, which will be used in the labeling process, there might be some moderate error in the labels, right? So you should not make too much into the accuracy or the lack of accuracy. The other one, which we want to see how to use it, is there is one more set of rich data where you had 2000 images of general chest abnormalities. In fact, there is a larger set of data, about 1 lakh images also in this. So if you're interested in working on this problem, then we can talk about it, right? But for purposes of the lecture, I just used a smaller set of data of 2000. Right? So now the question is, can you utilize this information to improve this learning problem, right? Now here you have only 600 images. So obviously this classification problem will not be that rich. Right? Okay, so that is the problem that I want to discuss. So any suggestions on what you should do? So remember that before you're tackling the problem, there are multiple things that you have to take care of, right? Like what is the pre-processing steps? What sort of data augmentation that you would do? What is the network architecture that you would use, right? What is the resolution you're operating in? What else? What is your validation scheme, right? Those you have to factor in all those before you build a solution. Okay, so any questions on transfer learning or this case study before we go into the notebooks?
So typically in medical imaging, in this case X-ray, right? So there could be more than one disease. There could be more than one issue. So does the algorithms today that you design can predict more than one, or you would be always focused on one type? Or in this case, just focusing on that, or?
No, see, ultimately when the product is deployed, right? So if you're just building a TB and a non-TB classifier, it is not useful because when the same patient comes, he may not have TB, maybe he has cancer. So if you miss it, you will be sued, right? So which means that the ultimate end state for the algorithm is a high accurate one, which can also identify diseases the same accuracy as a radiologist. But today, most of the algorithms will be point based. So the way that you will deploy it is you deploy it in a scenario where this can be standalone. Say in a TB hospital, right? In a TB hospital, most of the cases which comes in will be TB case. You know that just TB versus non-TB is. But if you deploy this in a general hospital where screening studies happen, then you will run into problems, right? So you choose the domain where it is to be deployed so that it limits the scope of your problem. Right? So that is a thing. But yeah, typically in all of this, it'll be a multi-label problem rather than a multi-class problem. Similar to image captioning, right? We'll have it. Okay, so the first experiment that I did was let us just go through this. So I downloaded the data from the open source and saved it in this H5 format, processed it and saved it. So this has two things. It has the image data as well as the ground truth, right? I hope everyone can see it now.
Yeah.
So this, so if I look at this data, yeah, it is like this, right? So total number of data I have for this is 662 images of 512 dimensions, and ground truth is two labels, right? I know if it is TB or not. So the first column is an indicator for the normal, and the second column is for TB, right? So that is the representation which is used here, and broken into. So if you look at the class distribution, it is more or less evenly balanced, right? It is 326 normals, and you have 336 TB cases. Right? So it's more or less well balanced here. You will have to look at, so the few things that you can do is you can look at bagging techniques, or you can look at dropping some of the samples, or you can look at data augmentation, few of the things that you can do. Or you can also change your class weights. So if you have like a multi-class problem, so you, in your loss function, you have to encode the class weight, which is inversely proportional to the number of samples you have. And also sometimes you'll see that, you know that a few of the samples that you have, your ground truth may not be reliable, right? So for that, you can also give a sample-wise weighting. So for all samples where you know the ground truth is reliable, you give a higher weight than samples which you know. Many of the cases you know, right? You know if the ground truth is reliable or not. Okay, so yeah, that is the description of the data. Then this is a pre-process that I'm using here. One is I'm resizing just because I wanted to do the experiment quite quickly. I'll try and scale this up to a higher resolution, right? The next time we meet. So I operated on a resolution of 92 by 92. I see that it's not good enough, right, for this application. But then for purposes of demonstration, this is sufficient. Then so for this, yeah, first is a resizing operation using OpenCV, right? Then this is a histogram equalization. Have you used so you can try using this when you look at this data, when you look at this notebook, just try to plot both the images, right, before and after histogram, see what difference it makes. When you try running without histogram equalization, you see that it will not be learning, right? So that's why I found that was a key thing to use here. So you have to frequently be using OpenCV and SK image. These have most of the things that, and people who are working with medical data, there is one more thing called simple ITK, which can also be imported, right? That also you can use. So next step is just whitening it, right? Subtracting mean subtraction and dividing by standard deviation. Then normalizing it between 0 and 1. Right? These are some standard things that I did. So which means that now the data, entire data, which are 662 images of size 512 by 512, is passed through this pre-process block, and now you have this pre-processed data coming out of it, which is images of resolution 92 by 92, histogram equalized and normalized, and so on. Okay, this is one more thing that we need to take care of when you're working with networks which have worked on computer vision problems, right? You have to convert this grayscale image into a RGB image, because each of these expect an input of 3 channels, right, for RGB. So you just replicate your grayscale image data into 3 channels and then create a new data with this. So now this process, if you look at this process data, it looks like this. So there are 662 time points, 662 data points. Each one is of spatial resolution 92 by 92 and 3 channels, right? Same, yes. Because the original data itself is a grayscale data only. So you just, in order to use these ImageNet based networks, you have to do that. Yeah, so this is how it looks. Yeah, you see that the resolution is pretty poor. So, but you see that even in spite of this resolution, it achieves some sort of an accuracy. So maybe at least a gross set of abnormalities it is able to detect. Then you do using histogram equalization. Yeah, that's it. You can also try a local mean subtraction. So what you do is you just apply just low pass filter on the image and subtract it from the original image, right? No, but just use histogram equalization. That'll work. That should work. Huh? No. See, there are local versions of histogram equalization. You can use that, but those are too expensive. So when you're running it on thousands of data, it might end up being, you'll have to run it overnight using multi-threading machines and so on. You can do that. But what you'd hope is when you have that large amount of data, you'd hope that DL will be able to learn some of those pre-process operations. So then you split it into train and testing, right? So I'm using a constant random state so that you can compare your experiments, right? So now the data that I'm using for training is 529, 92. Correct, right. So each time when you do this train test split, you will get the same set of samples. That is the idea of doing this. So you have to always set the random state to some constant in all your code. Make sure that you set it to some constant. This is just the dynamic range. It is between 0 and 1. Now, because I had very little data, only about 550 or so, you can only train a very shallow model on this, right? You cannot hope to go for a deep model. So I use a shallow model to this just with 4 convolutional blocks and then 2 dense layers, and used categorical cross entropy for this, and then data augmentation. So these are very standard things that I use for building this. Then what we should compare is if I go down, so when you plot, so this is the AUC, the test AUC that I've plotted here. It is around this is a decent 80% here, right? For whatever shallow network that I've trained on 92 by 92 on you cannot productize it without no, but a lot of them they're see that in machine learning you can trick the validation score, right? So what you do is if you get some difficult classes, you can throw away those difficult classes and just put just easy. You will get 95%. So a lot of startups are doing that, but that has kind of raised the expectation of the field. But even 85% is really hard to achieve. I can guarantee you that. But it depends on the domain also. Say something like fundus imaging. Fundus is the other image that you saw, right? It is a microscopic image of the cornea. So for that, typically you can get 95% AUC pretty easily. More detailed and a lot of the diseases are in vessels and so on. Yeah. There is some open source data. Fundus, I'll get the. Yeah. So that you can just use deep learning. There is open source data from, I think, shared by Google. Google has built this algorithm for diabetic retinopathy, right? So I think they have shared some open source data. You can use that for your experiments. So now the question is, can you transfer? So I wanted to see how to improve it, right? No, but what happened is I was struggling the whole of yesterday night and this morning, trying to transfer from ResNet and VGGNet and so on. So for some reason, the training was not even progressing. I think it is more on the way the array, ordering or something on that sort. I'm still working on that. Hopefully, for the next session, I'll be able to transfer it from a ImageNet. So, but then I ran this transfer learning in a more controlled setting where I borrowed the data from a similar domain, but on 2000 examples, and then learn from that and see how to transfer for this, right? So let us go to that other problem. Yeah, so there is one more data that I had from 5 class diseases. So this had a bunch of normals and 4 types of diseases in the chest X-ray. So then, so about 2000 of them. So 2000 of resolution 256 by 256. Then what I did was I collapsed this into just normal and 2 diseases. So that's why I have an array of 3 here. So similar, see, the thing is, when you're doing transfer learning, you have to make sure that the pre-process steps are same, right? So in all of your pre-trained networks like VGG or the other things, there will be a pre-process function they share. So you have to apply your image through that and then pass it through training, right? So in this case, it is on a control setting. So I use the same pre-process function for both of this. So that the appearance is more or less standardized, right? And then did the same thing on converting this into RGB. Yeah, so the images look something like this. So you see that in TB, you will have a lot of texture here, but whereas in this image, you might have the cardiac region slightly blown up, or you might have a lung collapse and so on. So it's a different problem. You can think of it as a more domain adaptation type of problem, right? Yeah, so finally, the number of training data here was about 1,500, 92, and then three channels. And then I trained a shallow model from scratch, the same model. But here the difference was that, it's the same model. Right? Then, here for this problem, for identifying normal versus abnormal for these general chest diseases, I got about 87% AUC. So remember that for the TB case, I initially got 80%. So now we want to see if we can use this model to bump up the AUC in the other model, right? That's what we want to do now. So I save this model. So you just you save this model. So when you're working with general model like BGG or something, you can import this model through Keras. Just one line command, you can import the model and weights, right? So here I save the model and then read it in this other notebook. So transfer from chest X-ray general disease model, right? So the goal here is, can we improve the TB classification accuracy by looking at the data from the adjacent problem, which is general diseases, right? So here I load the base model here, which I trained on the other 1,800 odd data, and then just visualize. So it's a shallow network with about 5 convolutional layers and 2 dense layers, and total number of parameters about 7 million. Right? In all transfer learning problems, one thing you would do is you have a base model, right? You have a base model. If you remember that chart that I showed, there is a source domain will have a convolutional block and you have a dense block, right? So that convolutional block, you need to pull out an appropriate layer from which you want the features, right? So in this case, I pulled from the base model or the source domain model, I'm pulling out the output of this layer called flatten 7. So if you look at this, so I'm pulling out the output from here, from this layer, which has 14,000, the feature vector here is 14,000 dimensions, right? So I'm pulling this and then attaching this into a new network. So the way I create this new network is as follows. So this is called as last. So from the base model, I'm extracting this, the output of this layer, and then passing this through my own new network structure here. So this is passed through a dense layer of 512, then add a dropout and then a dense prediction here. So the goal of this dense layer would be to classify into TB and non-TB. Right? Okay, so this is the one-line command that you need. That one-line command that you need to use for doing transfer learning. So you just set. So in this case, what I've done is I've set the convolutional layers to be false, the trainable to be false, which means that the optimization algorithm, when it trains across epochs, it will not train on the convolutional blocks, it will only train on the dense layers. So the idea of doing that is your domains are more or less the same, right? Your domain is exactly the same, which is X-ray, chest, and so on. So a lot of the bottom features will be same. Now, if you suddenly try to train the entire network, then you're losing a lot of information you have learned previously, right? So that's the motivation for holding your convolutional layer fixed and then tune only your classifier. Right? So first you do that. To do this, you use this simple one-line command. So now if you look at the model summary, the same, you have 5 convolutional layers and then 2 dense layers. But here, you see this non-trainable parameters is 16,000. So the 16,000 parameters are what comes from the convolutional layers, and rest of the huge burden on the network is from the dense layers, right? So which is modeling the classifier, right? Okay, then similar to the previous, this I hope you're familiar, right? The data augmentation, you can specify different ways of doing this. So in this case, for the X-ray case, I only use width shifts as well as height shifts. I've not used flips, but probably you could do the horizontal flip. Certainly not a vertical flip. So choose a data augmentation which is relevant for the problem, right? Then you do a data gen.fit so that it can throw this images at each mini batch, and then you call this model.fit generator command, right? So I hope you're familiar with this to use data augmentation. So I ran it for 20 epochs, and then when I plot this, yeah, this gives a jump about 3% in the AUC. Right? So you see that without transfer learning, it was at 80, and with it gave 83. You'll see some. When you play around with this a little bit more, you can get it to a more dramatic performance. But just a baseline gave this, and I think if you use some state-of-the-art network like ResNet or something, you will probably be able to get a better performance, right? Maybe closer to 87 or 88. The other possibility is you can fine tune all the networks, right? So in this case, what you do is you again use that one-liner and then set all the layers to be trainable. So now you see that number of in this model summary, the number of trainable parameters is a entire set of parameters. So you want to keep check this whenever you're doing before you start your training, right? And same thing, you do this, you do the data augmentation here, fit. Here, you need to be a little bit careful about choosing the optimizer setting. So if I blindly use Adam with a large learning rate, then it'll just throw off your learning process. So you want so typically when you're tuning your high layers or lower layers, you want to use a smaller learning rate. And also look up, see if there is some online help for Keras where you can do differential learning rate. That typically gives the best results. In Keras, there is no easy way of doing a differential learning rate. So what you want is you want to have a learning rate which is starting with a high value at the bottom, at the top, and then progressively reducing, right? So you need to find some way of doing it within Keras. There's no straightforward implementation in Keras for that. Yeah, now I trained on this. Yeah, I didn't get much of an improvement by fully learning. I guess the reasoning here is that the domain is more or less the same, so it would not have learned that many features. The other possibility is I have not used the differential learning rate. So this learning rate is probably too small. The learning rate I used was 0.001, right? It was very small, so hence it did not learn that much. But yeah, just like a point, only in a decimal type of improvement on this. But yeah, this just to demonstrate, how what gain you get. Yeah, you can definitely do better here. So what you should try in the lab is maybe the next time around I'll figure out what is wrong here and then see if I can use a ResNet 50 for this. But maybe in the lab, I think the plan is for you to do transfer learning for the dog breed classification. At least see whatever you already have a model for, and see if you can utilize transfer learning to improve the results, right? So that is the plan, I think. Yeah, that's all I had for this session. Any questions before we close? We are still discussing most likely object detectors. Okay, thank you guys. See you.